Hey everyone, welcome to this Mometrix video on organic acids. Let's start with a general review of acids. An acid, by the Brønsted-Lowry definition, is a compound capable of donating hydrogen ion, H positive. Remember, when hydrogen loses its electron, only a proton remains, so we'll often refer to the hydrogen ion as a proton. This is represented in the formula Ha plus B results in A negative plus Hb positive. Ha is the acid and B is the base. Ha donates the hydrogen ion, keeping the electron for itself, which results in a negative charge on A. We call A negative the conjugate base of Ha because it now has the potential to accept a proton, the Brønsted-Lowry definition of a base. Conversely, when B accepts the proton, it becomes Hb positive, which is the conjugate acid of B. Of course, not all acids are created equally. Some are strong and some are weak. A strong acid is more likely to release its proton, whereas a weak acid is less likely to release its proton. The strength of the acid is dependent on the stability of the conjugate base, A negative. If A cannot effectively stabilize the negative charge, it will be less likely to release the proton in the first place. Consequently, the best way to assess the strength of an acid is to consider the stability of its conjugate base, and we'll do just that when we consider the strength of organic acids. We measure the strength of an acid using the pKa, the acid dissociation constant. Briefly, the pKa represents the amount of acid that dissociates in water. While a more thorough derivation of the pKa is beyond the scope of this video, for now, just know that a small pKa is associated with a strong acid and a large pKa is associated with a weak one. Now that we've reviewed the core concepts related to acidity, let's move on to considering organic acids. Organic acids are simply acids where the A in HA is an organic compound. Let's consider some examples. Acetic acid, methanol, and methanethiol all possess acidic protons, hydrogen ions that are easily donated. These are highlighted in blue. The A portion, the organic frame, is highlighted in yellow. You'll notice, however, that while all these compounds have carbon frames, none of the acidic protons are actually attached to a carbon atom. Instead, they are attached to oxygen, sulfur, or nitrogen atoms. While there are some exceptions, the acidic protons on organic acids are usually bonded to heteroatoms, an atom other than carbon or hydrogen. To understand this, let's consider the conjugate base of the acid, A negative. When an acid donates a proton, the remaining electron is localized primarily on the atom the hydrogen was just bonded to. Because of their electronegativity and size, oxygen, sulfur, and nitrogen can all stabilize a negative charge better than carbon. Let's consider methanol and methanethiol as examples. If you removed one of the methyl hydrogens from either methanol or methanethiol, the negative charge would be left on the carbon. Carbon is too small and electropositive to stabilize the negative charge, which means these structures are high in energy and thus very unlikely to form. On the other hand, if you remove the alcohol or thiol proton, the negative charge would be localized on the oxygen and sulfur, respectively. For methanol, because oxygen is more electronegative than carbon, the conjugate base is more stable and lower in energy than when the negative charge is on the carbon. For methanethiol, while sulfur and carbon have the same electronegativity, the negative charge is distributed over a larger area, which has a stabilizing effect. This is because sulfur is a larger atom than carbon. Thus, because the conjugate bases are more stable when the negative charge is localized on the oxygen and sulfur, the alcohol and thiol protons are more acidic than the methyl protons. However, while the methanol and methanethiol protons are more acidic than the methyl protons, generally speaking, it's not very stable to have a negative charge localized on a single atom. Consequently, stronger organic acids have ways of spreading or delocalizing the charge across multiple atoms. This is achieved through resonance. Let's consider acetic acid to explore this concept. When the proton is removed, we can draw the negative charge localized on that oxygen. However, with some arrow pushing, we can move that charge to the other oxygen. This is a resonance structure. Regardless of whichever oxygen we decide to draw the charge on, in reality, that lone pair is spending time on both oxygens, which stabilizes the conjugate base, making acetic acid a much stronger acid than methanol or methanethiol. In fact, pretty much any organic compound with a carboxylic acid will have a fairly acidic proton. After all, it's in the name. Comparing the pKa's of methane, methanol, methanethiol, and acetic acid, we can see the importance of having a stable conjugate base for stronger acidity. Remember, these pKa values are for the specific proton that is removed. Knowing what molecular structures lead to an organic acid can be really helpful when you're assessing what chemistry is possible between different starting materials. Always be on the lookout for protonated heteroatoms, carboxylic acids, and other pi systems that allow for the negative charge to be delocalized. Before we end this video, we have one last important point. Remember that when we talk about these acids dissociating to H positive and A negative, we're talking about this happening in solution, usually in water. Charged particles are always high in energy, even if the charge is delocalized across lots of atoms. None of the acids we discussed today would ever spontaneously dissociate in the gas phase. The dissociation happens because the solvent molecules create solvent rings around the charged particles and lower the energy of the system with lots of intermolecular interactions. All right, let's finish with a review of what we've covered today. We reviewed the Brønsted-Lowry definition of an acid as well as the acid dissociation constant. We then defined organic acids as acids with a carbon frame, but noted that the acidic protons are rarely attached to carbon atoms. That's because carbon cannot stabilize a negative charge as effectively as larger and more electronegative heteroatoms. This led to our final discussion on what structural features lead to strong organic acids. Thanks for watching and happy studying.